All right, so for the interest of time, let's start going through it together, what we should do. So we said to figure out the delta heat of formation for our reaction that we have to sum up our standard heat of formation of our products minus reactants. And so that includes accounting for the molar amounts there. And so let's start with our products. So we have water, and then note the states too, so be careful with that. So we have H2O in the gas state, and so let's see if we can find. So here's water in the gas state, so negative 241.8. So negative 241.8, so times 6 plus our NO. Let's see, we have NO, so it's in the gas state, that works, so 91.3, and then times 4, since there are 4 of them. And then, so now we have to do minus the reactants. So oxygen in the gas state, that should be 0. Yes, so oxygen gas state, so we expected it to be 0, right? That's what oxygen is. And so I'll just do minus 0, not that that matters. And then ammonia, where's ammonia on here? So NH3 in the gas form, so it's 45.9, or negative 45.9, but then minus a minus, so that would be plus 45.9 times 4. So again, depending how you do your parentheses, could look slightly different. And let me re-pull up my calculator after crashing my computer. So now we have 241.8 times 6 plus 91.3 times 4 plus 45.9, since I already accounted for the sign, times 4. So did we get this answer? No? Did I plug something? Oh, yeah. I was saying that does look a little high. Okay, is this what people got? No. Man, I have calculator fail. Oh, yep. All right. Epic fail today. I dropped a sign. Okay, is this what people got? Yay. All right, thanks for checking me. I get a negative because I accounted for all the signs when I was doing them, even though I couldn't enter them properly. And so our delta heat then for our reaction is negative 902, and then that should be kilojoules. Yes, kilojoules. So are we all okay with this? And so again, enthalpy change in our chemical reaction is an extensive property. So again, it depends on the amount. So the more reactants we use, the larger the enthalpy change. And again, you saw that in lab with your little magnesium and dissolving it. And so that's why we also use a small amount. And so by convention, we calculate the enthalpy change for the number of moles or reactants in the reaction as written. And so all this is saying, lost the arrow there, is so how this is written, we have 1 mole of propane reacts with 5 moles of oxygen to give us 3 moles of CO2 and water. And so that means that we could either say, right, 1 mole of propane for our reaction has a delta H of negative 2,044 kilojoules per mole, or 5 moles of O2 is equal to that. So then, of course, you could divide by 5 to figure out the difference for 1 mole. And so now, see if you can combine a little bit of stoichiometry plus your delta heat of formations. So we have a gas tank in our home barbecue, contains 13.2 kilograms of propane. So calculate the heat in kilojoules associated with the complete combustion of all the propane, and you're given this reaction. So again, the key point is, well, I know 1 mole of propane produces this much heat, so how much does that produce, essentially? So I'll give everyone at least a minute or two to start it, and then we'll go over it. So for the interest of time, let's just start going through it together. So first, let's do our stoichiometry. So I'm just going to convert kilograms to grams, because I need to figure out, well, how many moles of propane do we have? And does anyone have the molecular weight of propane? .097. So let's divide. So 44.097. So then this gives us moles. And then we can say, well, for every 1 mole then, propane, we get out 2,044 kilojoules. And so let's plug this all in. Hopefully I won't do a bunch of typos this time. So 13,000 grams divided by 44.097. Oh, see, I already did a typo. So then we should have about 300 moles of propane in our tank based off of our equation. Again, just multiply by 2,000 now. And of course, that's a negative sign. And it's in kilojoules, so now we have 611 kilojoules. I guess we can round to 612 then, 1,000 kilojoules for that. Oh, yeah. So questions on this one? Or divide?
Or divided by that, and then what did you divide it by the -2?
Yeah, then I just multiplied. Yeah, so you could just kind of check yourself. You should have about 299 moles at this step. And then again, you're just comparing your mole-mole ratios. Well, for every 1 mole of propane, we get out negative 2,000 kilojoules of heat. So then we have to factor it, well, if we have almost 300, multiply it by that to get our total amount. And that should make sense, right? Because if we have a lot of moles in there, and you're going to do a lot of barbecuing, hopefully, with 13.2 kilograms, and so you're going to need to produce a lot of heat to cook your turkey or your onions, whatever you're roasting on the grill. Question?
How did we get to the 2044 kilojoules?
So this would just be given to you in a reaction. So, right, you have to be given some information. This is what this reaction does. This is dependent on the molar amounts, and then you scale it from there. Or if it was being like really tricky, then you might have to figure this out from your like standard heat of formation. So you could do that, right? So if it didn't give you, we could calculate it from our products minus reactants, figure this out, then figure out the molar amount. That'd be a pain.
Would you
But
do that on the midterm?
I don't know. I need to look at the last year's midterm and figure out how I'm going to modify it. I'll try to make it easier.
Thank you.
So enthalpy change, we mentioned, again, this is heat evolved at constant pressure. This is just repeating, so heat is a state function. And so if P is not constant, how do we calculate our energy? And so this means we get this little equation here. So previously, right, we had said this was our work done was just our pressure times our change in volume. But now, what if we have a difference in pressure? So we're either, right, making or destroying molecules of gas. So that would be one way to get our change in pressure. And so that means that your new change is going to be equal to the sum of the stoichiometric coefficients of your gaseous products minus the sum of the stoichiometric coefficients of your reactants. And so that gives you your change in gas. And then we have, so this is derived from PV equals nRT. So then you can calculate now your P delta V from this, essentially. So there's your RT. And so T has to be in Kelvin, or else it won't make any thermodynamic sense. And then R should be 0.0821. Oh no, wrong R. My bad. So R is this one, 8.314, so joules per mole Kelvin. And so notice that that's joules, not kilojoules. And so if we look at this reaction then, and so let's go through it together. So then our delta V gas here is equal to, so it says sum of the stoichiometric coefficients of gaseous products. So looking at this reaction, how many gaseous products do we have though? So 0. So 0 minus, and then how many molecules of gas do we start with? So look, yeah, so 3, exactly. So the sum of our stoichiometric coefficients, so 2 plus 1, that gives us 3. So basically, right, we have a change in 3 molars of our gas volume. Just think about that, right? Like you started with 2 moles equivalent of H2 gas, oxygen, you reacted them, you made a liquid though, so now your pressure would be dropping. And so then we can plug that in to get our work done. So it's equal to -3 then times R, so 8.314, and then times T. This one didn't say what T was at. So I'm going to assume in this case that it was like room temperature. So probably 298 Kelvin or so. So times 298. So we have -3 times 8.314 times our temperature. And then that gives us our work done, again in joules now. So -7,432 joules then. And so this is kind of back to Hess's law and what we saw in lab. And so Hess's law basically says that since our heat of formation, right, that is not path dependent, it means that we can essentially sum it up as a series of steps. So again, that's what we did in lab. We summed up one reaction as a series of 3 steps. And so all this is saying is the change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. So we have here A plus 2B. So looking like we get to D at the end. So first we could go A plus B to give us C, then we go C to D, but all we care about is just the ultimate change at the end. So we can add up all those processes. And so now this should hopefully look familiar-ish from lab. And so now we are interested in this delta enthalpy of formation. So we want to know, what does it take to do this? So again, doing your standard reaction, right? Your 3 equivalents of carbon plus 4 equivalents of H2. We could just magically smush those together to make propane. What would the delta heat of this reaction be? And of course, the tricky part is we can't observe this directly, right? We can't just do this reaction. That wouldn't happen. So to get there, we have to do steps that we do know. So we can figure out the combustion of propane. So that's given out here. This is also known. And this is also known. So take a few minutes. How can you add these up to get this overall reaction? And then, of course, tally up your delta H values. So I'll give you like a minute or two head start before we go through it. So again, not trying to rush, but so kind of the first thing that I would try to do is, right, we have our reactants, so we have our products, so we want to get at least the correct molecules on the correct side. So what I would try to do is, what happens if we flip the first equation? And so I'll just rewrite that starting out. So 4 waters plus 3 carbon dioxide gives me propane plus 5 equivalents of oxygen. And then I'm just going to go ahead and bookkeep with my enthalpy so I don't forget. So we flipped it. So now it's positive 2,043 kilojoules. And so let's see what else we could do. So I need carbons, and I need 3 of them though. So what if, again, I'm not sure, so I can multiply this by 3. And let's see if that helps us. So now 3 equivalents of carbon plus 3 equivalents of oxygen gives me 3 equivalents of CO2. And then if I multiplied that by 3, again, I don't want to forget my bookkeeping. So let's multiply our delta H by 3. So now we get that this process is equal to negative 1,180 kilojoules. Okay. And then, so before I try to add them, let me account for the hydrogen first. And so right now I have no other hydrogens anywhere. It's only in this equation. I need 4 of them. So let's just see what happens. We'll have to multiply this times 2 to get us to 4. Again, I'm just looking at this equation. And let's see what that looks like. So 4H2 plus 2O2 gives me 4H2O. And again, I don't want to forget, so let me multiply this now. So negative 483.6 times 2, so negative 967.2 for our delta H for this part. And so now the next question is, if we add all these 3 equations together, does it indeed give us what we want? And so we can just start by crossing out whatever is the same on the reactant and the product side. And right, so these are all your reactants. These are all your products. Make sure you're looking at all of them across all 3 equations. And so it looks like I have 3 CO2, 3 CO2. So I'm going to cancel that out. Did I write so? Oh, that's 3O2. I can't even read my handwriting. What else do we have? 4 waters, 5 oxygen, 3 plus 2 is 5, so that works. And then it looks like we are left with what we desire. So I'm just going to rewrite it. So 3 equivalents of carbon plus 4 equivalents of hydrogen give us 1 equivalent of propane. And so again, just double check. Yes, it matches with what we wanted, so that works out. And the states are also appropriate, so that's good. So remember in lab you had to account for the state change. And so since we can just add all these up, I'm going to add up all my delta H's, since again I already accounted for the flipping and the multiplying. So now all that's left is to add. So 2043 plus negative 1180.5. And make sure you guys watch me that I don't drop anything. So I get negative 104.7. Definitely check me out. So I see some nods. And so now we know then the delta H of this reaction, again, negative 104.7. Probably negative 104 or 105 with sig figs there. But, oops. So are we okay on this part? I definitely feel like this part will probably crop up on your exam, if I remember correctly. All right. Blah, blah, blah. Okay. So now all this is just, again, how do you write the standard enthalpy of formation? And so this is all I was saying earlier, right? Just magically take the elements, smash them together. What would you get? And so take a minute or two to do A and B. So what would that look like? Again, breaking it down just into the atoms magically and then smashing them together. If you could do that reaction, of course. All right, so let's go over what you wrote. So we should have something. So we have magnesium in our solid state plus carbon in our solid state plus, so we need 3 oxygens. I can't do math right now. So 3/2 equivalents, yes, that works. Plus 1 1/2 equivalents of oxygen gives us magnesium carbonate. So is this what everybody wrote? And whatever you have here, you should get it to just be 1 mole of whatever you're interested in. And so it looks silly too, right? Because again, you can't actually take these elements and burn them together and expect to get out magnesium carbonate. And then so your second one should look something like 6 carbons plus 6 equivalents of H2 to give us 12, plus 3 equivalents of oxygen. Again, if we could just magically smash all those atoms together, we get C6H12O6. Question?
What did you, or was the reason you put the 3/2 for oxygen?
Just to give me, because I only want 3 atoms of oxygen. So then 2 times 2 cancels that, so then that gives me 3 oxygen atoms. And so that's all you're doing, is how you can get individually these numbers of atoms. So that's why we have the 6 carbons, 6 H2 to give us 12, 3 O2 to give us 6. And that's all we need to write. It looks silly, but that's the definition. All right, the next important thing is bond energy. So there's another way that we can figure out the delta H of the reaction. And this is by comparing our cost of breaking old bonds to the income from making new bonds. And so we have our average bond energies, and so all these are calculated in the gas state, and this is homolytic cleavage, and so this means each bond gets half a bonding electron. So let's just go over what's homolytic versus heterolytic cleavage. So in your standard, like if we're looking at, let's just say methane or whatever, and then you're trying to break that bond. So homolytic cleavage, we use this little half arrow, and so that just breaks it evenly. Again, assigning each atom gets half of the bonding electron, so obviously a single bond, so each one gets 1 electron. So that's homolytic cleavage, and this is, usually the standard for almost every single bond, but there are a few exceptions that we've talked about before. They keep cropping up as good exceptions. But if we take these borane complexes, so this would where it would be not applicable, and this is heterolytic cleavage, just so you know. And so in this case, this is an odd one. So this is not a normal bond. So a normal bond is homolytic. See, that's just another name for it, normal. And so if we think back to the structure of ammonia, so we know nitrogen has 1 lone pair, so 2 electrons. And so in this case, right, boron, we know that boron tends to be electron deficient. It's in group 3. It can only make 3 bonds though, so then it's unhappy, right? It really wants that octet still. And so in this bond, nitrogen is providing all the electrons. And sometimes you see it drawn like this as well with an arrow, like if you look at papers. And so this is also known as a dative bond. And that just means that someone is contributing 2 electrons. And so again, this would just be a case where that would not be. So if you were to break this up in the gas state, it would cleave heterolytically, meaning nitrogen would gain back those 2 electrons. And so the other thing, see, this is why I don't like the order that we teach this class in, but again, we're not going to go into why I didn't change the order. But so, again, bond making is always positive, and so that's just two if you think of like the orbitals. So just most simply, you have H to make H2. That's going to drop it in energy, so this would be your bonding orbital. So that's, again, where that energy comes from. So you make a bond, that's a good thing, and you get energy back out. Except energy back out is going to be negative. So let's do more examples. And so to do these problems on your exam or something, so I am looking at least last year's exam, and so you would be given a chart of bond enthalpies. And so let's go through this. Let's go through this one first. And so to do these problems, I often recommend that you draw out all your reactants and products with the Lewis dot structure. And so here, let's look at our overall reaction. So we have methane plus chloride or chlorine gives us chloroform plus hydrochloric acid. And so to do these problems, you're analyzing, so which bonds get broken, which bonds get formed. And so again, breaking bonds requires energy, so you have to put energy in, so that's going to be positive. And so let's figure out what we have to break, and so you might want to draw these out like so then, at least initially, so you can clearly see, well, what changes? And so just looking at this, right, we still have 3 hydrogen or 3 CH bonds intact, but we did break one. So we need to break 1 CH bond. And then we had a chlorine-chlorine bond, and this gets broken. And then we form an HCl bond. So let's calculate that. And so usually I tally up kind of 2 sides. So I'll do first bonds broken. So that requires energy. So your sign should always be positive. And so now we just have to look at our bond energies and do it. So here's CH, so that's 414. And again, this is per mole, so it's just 1. So 414 is fine. And then we have to break our chlorine-chlorine bond. So looking at our chart, where's chlorine? Chlorine is 243. So now this is the total energy that went in. And so now let's see, well, how much energy did we get out, though? And so we formed, and so again, form now is negative. You're getting energy back. So we formed a carbon-chlorine bond. So let's see how much energy that was. So 339. Then we made an HCl bond. So that is, where's HCl? 431. So now we can add these two together. So 339 plus 431. So that's 770 kilojoules, and again, that's out, so that would be a negative sign. And now we can just add these two together to get our overall delta H of the reaction. So we put on in 657 kilojoules, we got out, I'm just going to subtract 770, and so this gives us the delta H of the reaction. And then so looking at our chart, right, it's showing that we're expecting it to be an exothermic reaction, So our products are lower in energy, and that matches our number. So our number is negative, so we know it's exothermic. Those products are lower in energy. And so again, we can say this is exothermic. And so if we were feeling the container, it would feel hot to us. So let's do this one together as well. Again, we're kind of running out of time. And so I would just do the same thing. Let's write out our reaction. So we have methane again, plus, so 2 equivalents of water gives us 4 H2s plus CO2. And so now we can figure out, well, what do we need to make? What do we need to break? And so just looking at our carbon, so our carbon went from being attached to 4 hydrogens to not. So we're going to have to destroy all these bonds. And then, so looking at our water, right, we don't have any oxygen-hydrogen bonds anymore. So we're going to have to destroy 4 oxygen-hydrogen bonds. But then in return, we'll be, again, forming now 4 HH bonds, and then 2 C double bond O. And then if you look at the chart, there's a little caveat here. So CO2 has a higher bond energy than just CO. So this would just be like for any CO bond. But then for CO2, you want to use the 799. And so again, let's do this one together for the interest of time. So now that you visually see what we need to make or break, let's add it all up. So we have 4 bonds of CH. So let's go where CH. Now I'm blind. There we go, CH. So 414. Now I'm going to multiply it by 4 though, right? Because we broke 4 of them. So that's 1656 so far. And then we had to break 4 OH bonds. They're all single bonds. So let's look at that. So OH, 464. So 464 times 4, 1856. So that's, again, how much energy went into the system. So now let's see how much do we get out. So 4HH. So we find our hydrogen bond. So 436 times 4. So now 1744 out so far. And then our 2 CO bonds, and again, using that special value, so 799 times 2. So 1598. And so now we need to add these all up and then add the 2 together. So I get 3,512 kilojoules were put in. So I put the positive sign there. And then bonds formed. Oops. And then 3342 out, so that's a negative since it's bonds formed, so we get that energy back. And so now let's just add them. And so I get 170 then.
Wait, why did you subtract
So last time I subtracted them because I added a negative. This time I just punched in the formed one first. So you could do, right, 3, 15, 12 minus 3. I think I plugged something in wrong. So you get the same answer either way. So 170 kilojoules then for this reaction. And so now this is telling you that this is endothermic then. So this reaction requires energy to go. Okay, questions on this one? And so the last page is just like how to do the calorimetry, which we did in lab. And I'm kind of going to rush through it. We can hit this back up on Tuesday. And so part of this is we calculated the heat from the specific heat. And so all this is, right, is a specific heat. So that's a measure of how much can a solution hold. And so I think for water it's like 4.18 joules. I just forgot the units for some reason. Blanked. Joules per gram degrees Celsius. And so your specific heat is what really drives this equation. So the reason why they have mass there in delta T is looking at the units. So if you're using this value, obviously it's grams, so that's why you have mass, Celsius. And so delta T, remember it's the same. So Kelvin and Celsius increase by the same amount. So like a change in degree in Celsius is just a change in degree in Kelvin. So the delta T doesn't matter too much whether you're in Kelvin or Celsius. And so just watch this. So if you, again, ask Google for answers, you could get specific heats in like molar amounts as well. So then you'd be multiplying by the molar amount, not the mass. And so we said, right, at constant pressure, then our delta heat of the reaction is equal to Q, which is, again, what you saw in your lab. And I think we are out of time, but this last bit should look just like what you did in lab. And so I'm going to stop here because we got to do some stuff. So don't run out yet. So your class kind of got screwed with all the scheduling. And so I have a quiz for you today. And so I will say, I know you weren't expecting it. So let's go over what's going to happen. So essentially, I say that I'm always going to drop one quiz. But then Dorothy and I talked. We didn't want to have you guys not have the opportunity to at least like even study with the quiz or anything. So what we're going to do, we're going to give you a quiz now. We'll give you another quiz next week on Tuesday. But because they're not your normal quizzes, we're just going to essentially drop them if they're lower. So you're going to end up with a total of at least 3 drop quizzes. And so I encourage you to take them. You know, if you do horribly, then they'll just be your drop quiz. They should not hurt you. But obviously, if you have other bad quizzes, then you might want to do them. And so I'm going to go ahead and hand out the quiz. If I could find it. I lost my brain this morning. Stuff from last week. So solution stuff, all the solutions, solubility crap. Some stoichiometry too with solutions. So I'm going to go ahead and hand this out. If you can do it and stay, please do it. And then otherwise, I'll see you guys in lab for those who need to do makeup. And then if anyone needs a calculator for the quiz, I can get a calculator. Oh, there's homework, so I'll hand out homework. All right, just in terms of quiz.
Oh, cool.
Lucky you. Well, there'll be 3 drop quizzes, so if you bomb it, then shouldn't be devastating. And I'll hand out homework if you didn't get it. You need homework. No, there. Yeah. You come to the lab, you can make it up. And then I'm going to hand back quiz 6. But I just want to make one remark because everyone didn't do this, so everyone got -3 points off. But for the last question of that one, it said, like, draw the Lewis dot structure for sulfate. And I wanted to at least see that you recognize that there's resonance to this. And nobody gave me a single resonance structure. And so I was looking for this, and then you could have drawn either this in a different orientation, so that would tell me that you know that there's resonance, right, and those double bonds move around. Or I saw this structure, which is okay, but again, you should recognize that maybe I could draw other things and other possibilities to get rid of those formal charges. So I gave you credit for this, but again, I still wanted to see some resonance. So I think everybody got that wrong. So don't feel bad, but that's what I'm looking for. So if it crops up again, I need to see some resonance if it has resonance. So obviously, a structure like methane would not have resonance, right? Because there's no double bonds, so you can't do anything about that. Okay, I'll shut up and let you work. And then don't forget your muddiest point, especially for Tuesday, so I know we should cover.
A question. You put this in milliliters, so I have to make it in liters, or is this millimeter moles? I'm just gonna guess that it's moles. Oh my gosh. Okay,
I would look at your mole highway percentage.
okay.
Open. Yeah, if you have to make that, okay.